so that we wouldn't get as much feedback. So I'm sorry to pull this on you guys last minute. Anyway, just thought it would be best not to be coughing all over you. So let me go ahead and share my screen. I'll put the notability stuff up and then it'll be just like I'm there. Except I'm a disembodied voice. All right, can you see?
Yep. Yeah, we can.
Okay, good. So last time we were talking about the effect of water on acidity, and there's this concept that we talked about called the leveling effect of water, where the strongest acid you can measure or have in water is H3O plus, and the strongest base you can have is OH minus. And we had begun talking about the impact of other solvents on the pKa of any given acid. And the issue is that most other solvents, organic solvents, are worse than water at stabilizing charges. So they're worse at solvating conjugate bases and counterions. And because of that, pKa's tend to be higher in organic solvents. Acids tend to be weaker in organic solvents. Differences in pKa's are larger and more accentuated in organic solvent because you start to see some of the more intrinsic differences in acidity rather than mostly the effect of solvent. And in general, solvents that are nonpolar will have acids in solvents that are nonpolar will have larger pKa's. So I'm going to show you a few examples, and there are going to be a few sort of principles that are illustrated by these examples. One of them is that poorer, let's see, that's not what I meant to say. Poorer solvation of conjugate bases makes intrinsic acidity matter more. Makes the intrinsic stability of a conjugate base matter more than in water. So as an example of that principle, excuse me, you can compare in water and DMSO the pKa's of these acids, and we can actually just look at the halogen series HBr, HCl, and HF. In water, you've got -9, -8, and close to 4, 3.2. In DMSO, the numbers are spread out even more. So in DMSO, the pKa of HBr is now about 1. That's dramatically less acidic than it would have been calculated in water, though remember that this acidity in water is a myth, right? Because if you put HBr in water, all you have is H3O plus and Br minus. Of course, in DMSO, HBr can persist a lot longer, but the value you get for the pKa in DMSO is still a little bit weaker than you could expect for H3O plus. I'm sorry. Let's see, for HCl, the pKa is like 1.8, and then for HF, the pKa is 15. So you can see that though the pKa differences in water do reflect the differences in stability of the conjugate bases, with Br minus and Cl minus being more stable than F minus. Nevertheless, those effects get bigger in DMSO. Sorry, let me get some water. Another example of this would be just comparing something like methanol and phenol. the pKa of methanol in water is about 15, whereas phenol is somewhat lower than that, about 10, because of the resonance stabilization of the conjugate base. But in DMSO, those pKa differences, oops, got them wrong. Those pKa differences are even wider. Oops, sorry. So you see the difference here in water. There's sort of a 5 pKa unit difference. Excuse me. Whereas here in DMSO, it's more like 11 pKa units. And this is, again, because water is not masking the, when you're not in water, the solvation due to water molecules tends to mask some of these differences in stability.
I have a question.
Yeah, go for it.
So does it just have to do with the fact that it's resonance? It doesn't really have to do with that it's bigger or bulky?
Yeah, so that's a good question. There's probably multiple things going on here. So size, I'm sorry, it's hard to talk. Size and acidity are somewhat difficult to tease out because there's a lot at play. So there are two general ways that size can affect acidity. First, we're talking about size of the atom that has the negative charge in the conjugate base. So without looking at, specific pKa's, there we go. We can say that HF is less acidic than HCl, which is less acidic than HBr, which is less acidic than HI. And that tracks with I minus being the largest conjugate base and F minus being the smallest conjugate base. And the reason that matters is because the negative charge on the conjugate base on the larger atom is spread out over a larger area of space. And we know from our discussions in chapter 1 and 14 that being spread out over a larger area of space is stabilizing, makes you lower in energy. The second way that size can affect things is just the size of the molecule as a whole. And here you got to be careful because it depends on whether you're in solvent or in the gas phase. And I wasn't going to talk too much about gas phase because as organic chemists, much of what we do is not actually in the gas phase, but it can be, it can be interesting to consider some differences there. Let's see. Yeah. So just considering the series tert-butanol, isopropanol, ethanol, and methanol in solution. In solution, methanol is the most acidic, and T-butanol is the least acidic. pKa for T-butanol is around 19. For methanol, it's around 16. But in the gas phase, it's exactly the opposite. So in the gas phase, T-butanol is the most acidic of this series, and methanol is the least acidic. And the reason for that is that when you don't have solvation to help you out, the molecule itself will start to compensate by spreading out, by allowing the negative charge on the oxygen to spread out through the whole molecule, just through in sort of an induced dipole situation. The more alkyl groups you have, the more electron density you have to move around to make space for the negative charge. It's almost, your text describes this as though the molecule was attempting to solvate itself because it simply has no other options. So in this sense, the size of the molecule as a whole, how does that affect acidity? Well, it depends on whether you're in solvent or whether you're in the gas phase. And we haven't said anything here about steric hindrance, which is something we sometimes talk about when it comes to bases. Sorry, Samantha, was that you?
What?
Did that answer your question? Was that your
yeah,
question?
Yeah.
Okay. Okay. Sorry. So one interesting thing about acidity is that, as we're seeing, it's environment dependent, and enzyme active sites can be way different than in water. Some enzyme active sites are nonpolar. Others have hydrogen bond donors and charges. You might imagine that in a nonpolar environment, a base might be stronger and the corresponding conjugate acid would be weaker. In contrast, if you have H-bond hydrogen bond donors that are present to help stabilize a conjugate base, perhaps an acid is stronger. Perhaps the conjugate base form is more stable. I'm really sorry. So here are some examples for the protein data bank of enzymes where active site side chains have pKa's that are substantially different from where they are in bulk solution. So as an example, the typical pKa in water of the glutamic acid side chain is 4.2. I'm really not crying. I know it sounds like I'm emotional, but I really am not. It's just sick. Anyway, this glutamate inside the enzyme has a pKa of 6.5. What does that mean? That means there's a whole bunch of pH values between 4 and 6 where this glutamic acid is going to have its proton instead of not. And this can be important for catalyzing very different reactions. Perhaps you need this glutamate to still be an acid in the reaction mechanism. So this is a case where the enzyme active site makes a group less acidic. Over here with acetoacetate decarboxylase, we have a case where the enzyme is going to make a molecule even more acidic. So this is a lysine side chain, and actually that lysine side chain is covalently attached via an imine linkage to a molecule that resembles the substrate for this enzyme. So we've sort of captured an intermediate in the process. But remember what you know about imines. They are formed when when amines act as nucleophiles to attack the carbonyl carbon. And for that, you'd want the amine to be in its neutral form, but you've got a problem because the lysine side chain typically at physiological pH exists in its positively charged ammonium form, and that has a pKa of around, I forget, 10 or 11. We'll say 10, or we'll say 11, who knows. However, within the active site, the pKa of that lysine side chain is 5.9, which means that now at physiological pH, the neutral amine form dominates, which is exactly what you need to have happen for the chemistry to occur. So, and there are tons more examples of this where you see side chains and active sites doing chemistry that it doesn't look like they should be able to if their pKa's were the same as in bulk solution. And the trick is that one major function of the enzyme, in addition to arranging the groups in the active site in a precise three-dimensional arrangement to catalyze the reaction, another function of the enzyme is to adjust the pKa of side chain functional groups such that they'll be in the correct form to do the reaction chemistry. All right, anything else we want to say there? Any questions you guys have? If you do, just shout it out because I can only see some of your hands. Okay. One of the reasons that we care about acidity is because acidity trends are sort of a good way to think about nucleophilicity. Remember that acids that are really strong are strong because their conjugate bases are stable and unreactive. And in contrast, acids that are weak because their conjugate bases are unstable and highly reactive. So those of you who are teaching 351 may already be using trends in pKa to explain differences in nucleophiles and in leaving groups. So as an example, you could use pKa arguments to explain why a nucleophile attacking and doing an SN2 reaction on methyl fluoride generally doesn't work because F- is a poor leaving group, whereas if we have CH3Br, that reaction is just fine. And that is because Br- is a good leaving group. What makes a good leaving group good? Well, a good leaving group is the conjugate base of a strong acid, because that's what makes the strong acid strong. HF has a pKa of 3.2, HBr has a pKa of -9. Okay, so we use pKa trends to talk about leaving group ability, but we can also use pKa trends to talk about the strength of the nucleophile. So if we want to know how strong a nucleophile is, that's the same question as asking if we have the conjugate base of that nucleophile, I'm sorry, the conjugate acid of that nucleophile, how acidic is that group? Okay. The challenge here is that there's more than one way to be a good nucleophile. All right. And we're going to talk in the remaining time before my voice gives out about something called hard soft acid base theory. And the idea is that This is like the first law of thermodynamics, or I'm sorry, this is like the first law of organic chemistry. Nucleophiles attack electrophiles. And the second law of organic chemistry is like unto it. The highest occupied molecular orbital on your nucleophile attacks the lowest unoccupied orbital on your electrophile. And all of this is just exactly like saying that Lewis bases attack Lewis acids. Now, the interaction energy this is how strongly nucleophile and electrophile are attracted to each other. Contains the following terms. First, you have to deal with the fact that even though one's a nucleophile and the other's an electrophile, each has a ton of electrons, core electrons that will repel each other. So this is sort of a constant term that doesn't change a lot. You just have to be aware of. And two atoms or two molecules approaching each other are always going to experience some repulsion, some electron-electron repulsion. This is like the Coulombic repulsion term in the Hamiltonian operator. Then there is an electrostatic attraction term. And this comes into play when the nucleophile is negatively charged and electrophile is positively charged. And in that case, that electrostatic attraction is just Coulomb's law. So that's K, some constant times the charge on atom 1 times the charge on atom 2 over the distance between the two. And this electrostatic attraction basically treats the nucleophile and the electrophile as point charges. Okay. Finally, there's a term which we're going to call overlap, which comes from overlap of orbitals on the nucleophile and the electrophile that allow electrons to be shared. Okay. And this term is concerned not with the charge on the nucleophile and on the electrophile, but it's concerned with the orbital coefficient on the nucleophile, the orbital coefficient on the electrophile, a term beta, which we don't need to define and you don't need to worry about and memorize it, but this is basically describes the extent of overlap in space, how well two orbitals overlap with each other. An example of that principle, as we've talked before, that end-on-end overlap in a sigma bonding case is more stabilizing than side-by-side overlap in a pi bonding case. And then in the denominator, you have the difference in energy between the two orbitals. So how far apart in energy the two orbitals are. Okay. So those are our two attractive terms in describing how nucleophiles and electrophiles interact. And it just so happens that these terms are somewhat at odds with each other. For example, if you're a nucleophile that is small and holds the negative charge tightly, probably the assumption that the nucleophile is a point charge will be pretty good. And so probably you'll have a high electrostatic term. But if you're a nucleophile that, again, has a negative charge held very tightly, probably the extent of overlap in space is not very good. Another way of saying this is that nucleophiles and electrophiles that have a high electrostatic term tend to be small. The atom that holds the charge tends to be small. It tends to be not very polarizable. That means it's unable to distort its electron density very much. The atoms tend to be that hold the negative charge tend to be electronegative heteroatoms. And because of that, the HOMO energy on the nucleophile is low, meaning decently stabilized. Charges that are localized generally fall into this category. Similarly, electrophiles that fall into this category have higher energy LUMO orbitals. Typically are on smaller atoms, also are fairly non-polarizable with localized partial positive charge or even full-on positive charge. And these types of nucleophiles and electrophiles will have a strong electrostatic interaction. And because of that, we're going to call the nucleophile a hard base and the electrophile a hard acid, a hard Lewis base, a hard Lewis acid, a hard nucleophile, a hard electrophile. And we're going to contrast that with soft bases and soft acids, or soft nucleophiles and soft electrophiles. Some examples of nucleophiles that fall into this category include hydroxide, chloride, alkoxides of any kind, ammonia or amines. And there are others, but in a lot of cases, these are first row nucleophile, or rather second row nucleophiles, where the negative charge is held on an electronegative heteroatom from the first row of the periodic table. Electronegativity, remember, means that the electrons on that atom are held close together, close to the atom, and lower in energy. Electrophiles that qualify as being hard Lewis acids include not a lot of things, actually. That you'll see a lot of ions. So this is kind of boring, right? Lithium, sodium, potassium could all be considered hard electrophiles, but also on this list are included boron-based electrophiles. And then another one that another few that you tend to see in like Friedel-Crafts reactions, aluminum is a fairly non-polarizable electrophile. Okay, so the reason that hard nucleophiles and hard electrophiles work and prefer each other is because their electrostatic interaction is strong, whereas the overlap term here would be, or rather the overlap term, think of it this way, the difference in energy between HOMO and LUMO is likely to be quite large for these hard acids and bases, so the energy of interaction will be small. You have a big number here in the denominator and probably a small number for beta, small extent of overlap in space because the charge is held on an atom that's electronegative and therefore close to the nucleus. So these electrophiles and nucleophiles, the only thing they got going for them is the fact that they've got concentrated charges that are attracted to each other. Okay, questions about that? I kind of stumbled through that, but that's the gist.
Okay, so the reason why, in essence, you're trying to say that the energy of interaction is low, but then they prefer each other because of the electrostatic, the strong electrostatic attraction that they have for each other.
That's right.
Okay.
So the overlap portion for these, they have the hard Lewis bases or nucleophiles and the hard Lewis acids or electrophiles have a strong electrostatic attraction for each other, probably a weak overlap, weak orbital overlap interaction. So you think of these as basically being point charges that are attracted to each other simply because of Coulomb's law.
Okay, so the reason why the orbital overlap is weak is just because of the difference in energy between the LUMO and the HOMO.
That's right. The HOMO and LUMO energy differences is large enough that the overlap interaction term becomes small. Also, this beta term describing how much the HOMO and LUMO overlap in space is very small for hard electrophiles and hard nucleophiles, because their orbitals are actually held closer to the nucleus. They don't stretch out in space quite as much. Now, Joshua, you've been doing some of this in inorganic. Is there something I'm missing?
No, it makes sense.
Okay.
It's just
All
with
right.
hard soft, would it just be basic hard? They say hard soft is unfavorable.
That's right. Yeah, hard soft
Just because they try
interactions
to
are.
split the difference, or
What's that?
is it because they try to split the difference between the two terms instead of?
Yeah, a hard soft interaction would have non-optimal attraction in the electrostatic term and non-optimal attraction in the overlap term. And so I suppose the combination of those two is not linear, and that when you mismatch them, the sum is not as great as it could have been if you had like interactions. Okay, so let's talk about the soft electrophiles. What do these tend to be? Well, they tend to be larger and more polarizable. By that, we mean they can distort their electron density easily from one side of the molecule to the other. By virtue of being polarizable, they would engage in better van der Waals interactions or induced dipole interactions. Typically, in this category, the HOMO and the LUMO of the soft nucleophile and soft electrophile, respectively, are close in energy. Large soft electrophiles tend to have delocalized lone pairs or negative charge or positive charge, depending on whether you're talking about nucleophile versus electrophile. Because HOMO and LUMO are close in energy, the EB minus EA term in the overlap energy is small. It's in the denominator, so that makes energy of overlap better. And we actually learned this in chapter 14 or wherever it was, that when we mix two orbitals together and they're close in energy, we get a more favorable mixing interaction. Soft nucleophiles or soft Lewis bases. Let me give you some examples of that. So these are all going to be larger versions of those second row nucleophiles. For example, thiolates, negatively charged thiols, actually neutral thiols and thioethers work as soft electrophiles. Iodide, phosphines, which is the third row version of the amine. Also, you could include benzene as a soft nucleophile. CN minus is a fairly soft nucleophile. And these aren't things to memorize, but you can see, sort of look at the difference between the soft nucleophiles versus the hard nucleophiles down here. The difference really is size. And the soft nucleophile is where our pKa intuition and ranking of strong nucleophiles goes away and doesn't actually give us predictive value, right? Because I minus is the conjugate base of a really strong acid, pKa minus 11. Well, then how on earth is I minus a good nucleophile? And the answer is because it's larger and more polarizable. And for corresponding soft electrophiles, its electrons are high enough or close enough to the LUMO in energy to make a favorable interaction. So you will encounter students that ask about this in 351, and I'm not sure in 351 you necessarily have the tools to explain why I minus can still be a good nucleophile. And the answer is there's more than one way to be a good nucleophile. The pKa trends are good at explaining which ones are going to be good hard nucleophiles. They're not that great at explaining which ones are going to be good soft nucleophiles. And then the soft electrophiles or soft Lewis acids include, as an example, things with polarizable low energy LUMOs. So the halogens, all really great soft electrophiles. Transition metals that have lots of electrons in them, but are nonetheless positively charged, can be good soft electrophiles. In fact, historically, the ability of sulfur-containing compounds to interact with mercury is important. Does anybody know what you do in a lab when you break a mercury thermometer? You run around panicking. Oh, I know. You pick it all up and then start to play with the mercury in your hand. That's a good idea, right?
Yeah.
No. You're supposed to, not a good idea. You're supposed to gather up all the mercury you can, but if there's little droplets that are in places you can't get to, you can actually sprinkle sulfur around, and the sulfur will bind to the mercury. The ability of mercury and mercury anions to bind sulfur is one reason why thiols used to be called, and some people still call them, mercaptans, because they capture mercury. I didn't know that. I thought that was kind of interesting.
Yeah, that's
Also on this list would be included carbines, and actually radicals can sometimes be considered soft electrophiles. Okay, so there's nothing to memorize here. I just feel like I've heard people talk about this before, and I never really understood it myself. So I feel like it's useful to see that there are two different ways to be a good nucleophile. Okay, so questions you want to ask there? All right, well, my voice is about to give out. What I will do then is I think Zoom has been recording this, so I'll post that video on YouTube, and let's see, I'll post the notes. I hope to be back Monday. Recall, as we said last time, that there won't be an exam next week, and we're going to try oral exam format the following week. So I'll give you an exam. I'll hand out an exam on not this Monday, but the Monday after that. Let me get a calendar in front of me so I can be precise. Yeah, I'll hand out an exam on Monday, the 25th of October. You'll have until Thursday to work on it. It's open book, open notes, but you have to work alone, not with fellow class members or former grad or grad students or your research advisor or anything like that. And then you'll schedule a time. I'll send out a link to a Google Sheet where you'll schedule a time on the 28th, Thursday, the 28th of October. Probably just a half hour to come in and discuss your answers to your questions. I will pick one to talk about in detail. You can pick the other. And I will assess your understanding based on sort of the same rubric that I used for your exam one. We'll see how it goes, and then you can tell me what you prefer. Any questions about that? Okay, I guess I just wanted to tell you one last story. So was it last month? Sometime last month, Amber, my wife, and I were headed into the temple, and we saw Dr. Patterson, James Patterson, coming out, and I said hi to him, and he says, "Oh, I was just finishing up my shift as an organist. I play every other week here." And I thought that was kind of cool. Later on, I saw him again at in the Benson building. He was told him that I was an organist too. And he says, "Oh, the lady that coordinates that is in our state. Do you want me to give her your number and see if you can get involved?" So I said, "Sure," and got trained on how to use the organ in the Provo Temple Chapel. And you're supposed to play kind of quietly, not loudly, and all this stuff. Well, they told me that actually playing the organ in the Temple Chapel, and it's like a 1.5 hour shift every couple of weeks, is a service missionary position. So I had to go through this process of submitting an application to be a service missionary. And then a couple nights ago, my stake president calls me in and says he wants to set me apart, but what the church has told him to set me apart as is as a senior service missionary. So I am 42 years old, but I am now serving as a senior service missionary, which I'm never going to hear the end of around here. My wife tells me I already shuffle around like an old guy. So there you go. Okay, that's it for me. I will see you guys on Monday. Have a great weekend.